Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 12th episode of my tutorial series on Z80 assembly language development, targeting the Sinclair ZX Spectrum to learn how to program a simple system starting at the very lowest level. If you haven't seen the earlier episodes, I strongly encourage you to go back to my channel, and don't forget to subscribe and click the bell to be notified when the next episode comes out, and start this playlist from the beginning. So far in this series, we have learned the basics of assembly language and how each instruction for the Z80 works. We have started looking into how the ZX Spectrum itself works, including the ROM routines and the graphics as controlled by the uncommitted logic array, or ULA chip. We have only worked with static graphics so far, and that's because things get a bit more complicated when you deal with the timing of the video signal. Dynamic graphics require you to use interrupts to make sure you are changing the contents of the display when it won't cause issues like tearing. In fact, any kind of timing requires the use of interrupts, and in this lesson we will go over how to work with interrupts in detail. The Z80, like the 6502, has two kinds of interrupts, each triggered by pulling a particular pin low during a rising edge of the CPU clock. The INT pin will trigger a maskable interrupt, while the NMI pin will trigger a non-maskable interrupt. The NMI has a higher priority, which means that an NMI can interrupt the handling of a maskable interrupt, but not vice versa. On the original ZX Spectrum, the only device in the system tied to the INT pin is the ULA, which will trigger an interrupt at the beginning of the video signal's vertical blanking period. For a PAL TV, we are dealing with a 50 Hz cycle, so we get a vertical blanking period before each interlaced field of each 25 Hz frame. This period lasts the equivalent of 8 scan lines before field 1 and 7 scan lines between field 1 and field 2. It is during this period where you can change the screen memory safely, and you won't be in danger of tearing between the last frame and the current frame. This gives you no more than 512 microseconds to get these changes made. That may be plenty of time for a modern CPU, but for a 3.5 MHz Z80, that's only 1,792 T-states, which could be as few as 100 instructions and no more than about 400. As for the NMI, the original Spectrum simply ties the pin high through a resistor, which means that NMIs won't happen unless you have a peripheral connected to the expansion port. Both the INT and NMI pins are routed there, so that device could cause its own interrupts, and if it triggers an NMI, the handler in the ROM at hex address 66 will run. Older Spectrum models will let an expansion device modify the memory map, so it could swap in its own memory and run its own NMI routine. For this episode, however, we will only be dealing with maskable interrupts from the ULA, as that is the only interrupt you can expect every user to experience. Now let's go back to review the IM instruction, which sets the maskable interrupt mode. Interrupt mode 0, as we've discussed before, is not supported by the ZX Spectrum, but now we should qualify that by saying it requires an external device to support it through the expansion port, but that is not very common. Mode 0 mainly exists for backward compatibility with the Intel 8080, and is really only good for triggering restart instructions, so we're going to ignore that as well. At startup, the Sinclair basic ROM puts the Z80 in interrupt mode 1, which means that every blanking cycle will start with a call to the maskable interrupt routine in ROM at hex address 38. But that doesn't do anything to help us with graphics, so for games we'll want to have a custom interrupt service routine. This means using interrupt mode 2 with the IM2 instruction. This will require us to build a jump table in RAM and set up the I register to use it. Where it goes in the jump table is a mystery, because while the ULA triggers the interrupt, it only reads from the data bus, so the value on there is effectively random. We'll see how to deal with that soon. But first, let's further review how to control interrupts. The EI instruction will enable maskable interrupts for the current mode, but only when an NMI isn't being serviced. As that's unlikely to happen at all, we're not going to worry about that. And like we saw before, none of the CPU flags are affected. However, that's a bit misleading. There are a couple of flip-flops in the Z80 that act like additional flags outside the F register. And EI works by setting both IFF1 and IFF2 to enabled. It's IFF1 in particular that enables maskable interrupts, and that will be automatically reset whenever an NMI is triggered, which is how the interrupt priority is enforced by the Z80. IFF2 acts as a backup so that when an NMI routine returns with RETN, IFF1 will be restored to the state of IFF2, re-enabling maskable interrupts if they were enabled before. But an NMI can disable future maskable interrupts with a DI, and then the old state will not be restored. This is because DI, beyond what we discussed before, resets both IFF1 and IFF2. This means that any DI must be followed by an EI before any maskable interrupts can happen again, even if it was done during an interrupt. You don't need to do a DI during any interrupt to prevent further maskable interrupts before the current routine is done. When a maskable interrupt is triggered, it acts the same as a DI, with both IFF1 and IFF2 getting reset, so doing another is just redundant. This also means that interrupts need to be re-enabled with an EI before you return from a maskable interrupt handler, if you want the next maskable interrupt to get handled automatically. To finish this review, let's look one more time at the 48K Spectrum memory map. Interrupt service routines need to be in a place that can contain code, obviously, and in the case of IM1, that means the routine needs to start at hex 38, placing it in ROM. So we can't change that, and unlike other systems, there's no RAM vector that we can overwrite to redirect away from the default ROM routine. Doing something different for IM1 requires a change in hardware, like attaching a device to the expansion port. So generally, if we want a custom handler loaded into RAM, we need to use IM2, which could have its handler anywhere in memory, but the jump table needs to take up a whole 256-byte page of memory, plus the first byte of the following page. And since nowhere in ROM has such a jump table, we need to place it in RAM. And it must not interfere with things like screen memory or basic variables if you're using the ROM. And you can't place it at the very end of RAM because you need to end the table on the first byte of a page of RAM and not roll over to the beginning of ROM at address 0. Speaking of the ROM, let's take a look at the maskable interrupt routine for IM1 at hex address 38. It nicely preserves AF, HL, BC, and DE on the stack, but not the alternate or index registers. It then increments a 24-bit frame counter at hex 5C78, so every 20 milliseconds it ticks up until it rolls over. A 24-bit counter means that it will run for over 93 hours until that happens, so it's fairly safe to assume that you won't see it happen during the run of your program. Then it scans the keyboard by calling the ROM routine at hex 02BF, which will place the code for a new key press in the last K variable at hex 5C08, and handle repeats for keys that are held down. Then it restores the registers from the stack, re-enables interrupts like it should, and then returns with an unconditional RET instruction. It does not use the RETI instruction, as it assumes that the device requesting the interrupt is the ULA, and it doesn't expect any signaling back after the interrupt handling is done. For your own routine, you can make the same assumption, and just end it with the same EI-RET combo. But before you can run your own routine, you need to set up a jump table for IM2. That means loading the page containing the first 256 bytes of the table into the I register. The vector that will be called will be at an offset into that table based on the current value on the data bus. Like we saw earlier, that value is effectively random because the ULA doesn't write to the data bus, so we need to make sure that each entry within the table is exactly the same, with 256 entries across 257 bytes. That last byte is the first byte of the next page, which will be used as the second byte of the vector address if the offset was 255, and the last byte of the previous page is where the vector begins. Being random, we have no way of knowing the offset will be even or odd, so the only viable solution is to make the vector have the same byte for both bytes, so that it doesn't matter what offset you start at. The least intrusive place to put the table, then, is on the second to last page in RAM, hex FE. This means we load FE into I, and then fill every byte from FE00 to FF00 with the same value. The least intrusive value would be FD, so that no matter where you jump from, you always get hex FD for your vector, and that will be tucked neatly behind the jump table. You only have 3 bytes, but that's all you need to have an unconditional jump opcode and an arbitrary address for the actual routine, which can now be anywhere in memory, even back at hex 38 in ROM, if you want to take the long way back to IM1. But obviously, you only go through this effort to place a RAM address there, and you can determine that address programmatically, or just by using the label for your routine in your assembly code, and let the assembler figure out what to put there. This arrangement means that you now have all the RAM up to hex address FDFC for your code, and all that you end up wasting is the 87 bytes between the end of your jump table and the beginning of the UDG character tiles. And you can always use that space for extra data, if you really needed it. Let's see a concrete example of this now, where we can use an IM2 interrupt to move a virtual sprite across the screen in response to the keyboard. We'll just make it a little ball and have it use the X and Z keys to move right and left respectively. Simple enough concept, so let's go right to the code. As usual, we start our assembly code file by specifying the 48K Spectrum as our target machine, and beginning our code at hex 8000. First up, we want to define some addresses that we need in our code. For our interrupt jump table, we define the starting address of hex FE00, like we discussed earlier, and then the vector value of hex FDFD, which we will use to fill up the table. We need one more address for the part of screen memory that we are going to be modifying. And for this program, we want the sprite to be within a single 8-pixel high character row. So we'll go with line 88, which has its bitmap start at hex address 4860. For our data, we want a RAM variable for the current position of the sprite, which is the x-coordinate of its left edge. While the sprite will always stay within a character row, it will usually be straddling 2 character columns, and the pixels for each line of the sprite will need to be spread across 2 bytes of screen memory. We add an extra 0 so that we can load the value as a 16-bit word when necessary. But as the highest possible position value will be 248, we can just treat it as an 8-bit value. Next we have the sprite itself, which is an 8x8 pixel bitmap. We can use binary bytes to define each line to better visualize the pixels in the assembly code. The last bit of data is a line buffer that we are going to draw the sprite in. To get 8 lines of screen memory, we need 256 bytes, which will initialize to 0 to make it all paper. Unlike the actual screen memory, this line buffer will have all 8 lines in contiguous memory, instead of being 32-byte lines spaced 256 bytes apart, as it will be in screen RAM. You could just make a complete alternate buffer of the screen RAM bitmap, but that would take up 6 kilobytes, and you may not need to do that in your application, especially if, like in this case, most of the screen rarely changes. To set up interrupts, first we need to disable them so that we don't end up flying into random memory on the next frame. Now we can build the jump table, so we'll set up a loop to do that. First we need to initialize some addresses, starting with the beginning of the jump table, which we load into DE. Then we load the vector address into HL. Now to get the jump table page into the I register, we don't have a single instruction that can copy a value from D to I, so we have to go through the accumulator. We also don't have a single instruction to copy H or L into the address in DE, so we'll load that into A, where it can stay for the duration of the loop. As H and L have the same value of hex FD, it doesn't matter which we use. In each iteration of the loop, we load that hex FD into a byte of the jump table. Then we increment the E register to point DE to the next address. We keep doing this until E rolls back to 0, at which point we have filled up the entire first page of the table. We have just one more byte to fill, but this time we increment D so that we get to the next page. And we know E is 0, so it will just be that first byte of that page, which happens to be hex FF, the last page of memory. We fill in that last copy of hex FD, and our table is now complete. Next, we have to put the jump instruction at hex address FDFD so that we can actually call our custom handler. That address should still be in HL, so we first fill in the opcode for an unconditional absolute jump instruction, which is hex C3. The Z80 expects that opcode to be followed by a little endian address, so then we fill in the next 2 bytes with the address of our custom interrupt handler, which we have creatively labeled IM2 handler. We don't need to know what that address will actually be when we write the assembly code. We can just let the assembler figure that out. All we have to do is load what that address turns out to be, starting with the low byte, and then the high byte, incrementing L each time. With that complete jump instruction now completely filled in and tucked right behind the jump table, we are ready to finally enter interrupt mode 2 and enable interrupts. Now for each frame, the Z80 will be able to pull the hex FD vector out of the table, regardless of the current offset, and execute that jump instruction. Even though we haven't seen that code yet, we know that it will be already loaded into RAM before we ever get to running any of our code. Now we are ready to begin the main thread of our program's execution. But before we get into that loop, we need to initialize the sprite by calling the drawSprite routine, which we'll see later. This will draw the sprite at the initial location we defined earlier, but only in the line buffer, not in screen RAM. That will have to wait until the interrupt. We start our main loop by waiting for the next interrupt to happen. We do this because we don't need to do anything until the last frame has been rendered. In theory, we could run more often, but it would be harder to time. Besides being the safe time to update screen memory, the interrupt is our best means of timing anything, and the best resolution we can get is that 20 millisecond frame period. So instead of checking the keyboard multiple times during a frame, we'll just do it once to make sure that the timing is more predictable. Since all we care about are the X and Z keys, we can just listen to hex port FE, which is connected to both of those keys, along with a few others. If a key is pressed, its bit will be pulled low, so if we AND that scan result with 6, it will isolate the bits for X and Z, which are represented by bits 2 and 1 respectively. If both keys are pressed, the AND instruction will zero out A, setting the Z bit. In that case, the two keys should just cancel each other out, so we just jump back to the top of the loop and wait for the next frame. If neither of them are pressed, both of these bits will still be high, so a comparison with 6 will also set the Z bit, and in that case, we also want to jump back to the top. If we made it through both conditional loops, then we know exactly one of the keys was pressed during the scan, and we'll use that to determine the direction of our sprite movement. But first, we want to load the address of our position variable into HL, so that we can use it as an effective RAM register. Then we check bit 1 from our keyboard scan to see if the Z key was pressed. If it was, the Z bit will be set, and we jump ahead to move the sprite to the left. Otherwise, we know that X was pressed, so we want to try moving the sprite to the right. But first we want to make sure that we aren't already at the extreme right end of the screen. Since we have a 256 pixel wide display area, a position of 248 means that the sprite is taking up the last 8 pixels of the line already. If the position is there already, we go back to the top. Otherwise, we increment the position value right in RAM and jump ahead to draw the sprite. If Z was pressed, we would have jumped to .go left, where we want to check to see if the current position is already 0. If it is, the Z bit will be set, and since we can't move further to the left, we jump back to the top of the loop. Otherwise, we decrement the position value and continue on to draw the sprite at its new position. Now in our line buffer, we'll have the old position of the sprite already rendered there. As you may remember, we jumped ahead to here at the beginning of the program to initialize the line buffer. Getting here again means that the sprite is now in a new position, so we'll have to effectively erase the old sprite and draw in a new one at the new position, which will be 1 pixel to the right or left. We can mess around with this line buffer at any time during the display cycle, as it's just in regular RAM and not in screen memory. And since we timed it out so that this change is happening right after the last interrupt, it will be done well before the next one. So let's start by loading the starting address of the line buffer into HL, and then the position as a 16-bit value into BC. As you remember, we set aside that extra byte to have the flexibility of using the position variable as either an 8-bit or 16-bit value. That's going to come in handy very soon. We want to adjust the address in HL to the byte in the line buffer that we want to update, and that will be based on the position. But since the position is pixel-based, we need to divide it by 8 to get the byte offset. So we just shift it to the right by 3 bits. We can just do this on the C register, as we know B will just be 0. Now we have the position value divided by 8 in BC, and we can just add that to HL to get the correct address. We'll need this address again later when we are using HL for something else, so we can copy it to the IX index register using the stack. Now we need to see if we need to clear any pixels in the previous byte of the line buffer, which would be to the left. This could only happen if we move to the right and the left edge of the sprite now starts in a new byte. We don't know any more which direction we moved, so we'll have to assume that anything is possible. So we check our position, and if it turns out to be 0, we know that we'll be at the extreme left end of the screen, so there won't be anything further to the left to erase, so we just jump ahead to start drawing. If we have a non-zero position, we need to see if it's evenly divisible by 8. We can do this by doing an AND with a 7 to check to see if the lowest 3 bits of the value are 0. If it's not 0, then we know that the sprite will start somewhere in the middle of the byte, and we won't have to go back to the previous byte to erase anything, so we jump ahead in that case too. If we haven't taken either of these jumps, we continue to decrement HL to point to the byte before the destination of the sprite. We want to make sure that the pixels to the left of the sprite are all cleared on each line, so we set up B to be a loop index, and we're going to do 8 iterations, one for each line of the line buffer. And we also set up DE with an offset of 32, as there are 32 bytes in each line, and our line buffer has all 8 lines consolidated together, instead of interwoven with other lines as they are in screen memory. So in our loop, we clear out the byte that HL is pointing to, then add 32 to get to the next line in the line buffer. We keep going, decrementing B and looping back until it gets down to 0, and the byte to the left of each line of the sprite has been cleared. Now we're finally ready to start drawing the sprite in the line buffer. We need the position value modulo 8 in A, and it may already be there, but it may still have the whole location value there, so we do another AND with 7 to be sure. This will give us the number of bits that we need to shift each line of the sprite. If the position is evenly divisible by 8, then no shifting is necessary, but otherwise we'll need to have the right end of the sprite rendered in a second byte on each line. We store that shift amount into B, and then load 8 into C to use it for a line loop index. Before we start that loop, we initialize HL to point to the first byte of the sprite we defined earlier. In the line loop, we load a byte containing a line of the sprite into D, and then 0 into E so that DE will contain both the sprite line and space to the right to clear out. Now we need to shift that to the right by the number of bits specified by the value in B. We load that back into A, which will be the loop index for the nested shift loop. If A is now 0, there's no need to shift, so we can jump ahead to just draw the line as it already exists in DE. Otherwise, we enter the shift loop and shift the value in DE to the right and decrement A, then keep looping until A gets down to 0. Now that DE has the 2-byte pattern we need to draw the current line, we can copy it to the line buffer by loading the value in D to the address in IX, and then E to IX plus 1. We don't need that pattern anymore, so we can just load 32 into DE to add that to the address in IX to make it point to the same offset on the next line of the line buffer. Then we increment HL to point to the next line of the sprite, and decrement C and keep looping the whole line loop, including the nested shift loop, until C gets down to 0, and all the lines of the sprite are finally drawn in the line buffer. With that, we're ready to wait until the next frame to do it all over again, and keep looping forever. Of course, while we wait in the main thread, the interrupt handler will be called at the beginning of the next vertical blanking period. We already set up the instruction at the interrupt vector to jump to IM2 handler, which we can just place right here. To make sure that nothing gets corrupted in the main thread, we store all the general purpose and index registers on the stack, including all the alternate registers. We aren't really using all of these registers in our program, but this is just good practice anyway. If you need more time in your interrupt routine, you can always cut out saving unnecessary registers, which in this case would be IY and all the alternate registers, which we don't use in the main thread. Now we can get down to doing the actual interrupt routine, where we need to copy each line from the line buffer to its final destination in screen RAM. While the line buffer is consolidated, screen RAM has the same lines interleaved with other lines, so we need to copy one line at a time. So we initialize our line loop by loading the starting address of the line buffer into HL, and the starting address of the corresponding lines of screen RAM into DE. We use B for the loop index, so we need to initialize that to be 8. In each iteration of the line loop, we start by initializing a nested byte loop, which will copy all 32 bytes of each line from the line buffer to screen RAM. so we use C for that loop index and initialize it to 32. We copy each byte from the line via the accumulator, as we can't copy from one memory address to another in a single Z80 load instruction. Then we increment HL to go to the next address in the line buffer, but then just increment E to go to the next address in screen RAM, because we know in that case that we won't be crossing a page boundary. That will have to wait until the next line, which we get to once C decrements down to 0 and we stop the byte loop. HL will already be pointing to the next line in the line buffer, but DE will need to be adjusted. To get to the start of the next line of screen RAM, we reset E to have the value it had at the start of the line loop, but then we increment D to go to the next page. This will effectively make DE jump over all the interleaved lines we don't care about and get to the line in screen RAM that corresponds to the next line of the line buffer. Then we decrement B and keep looping through the rest of the line buffer until B gets down to 0, and then our interrupt routine is done and the sprite is properly rendered in screen RAM. Now all we need to do is restore all the registers, then re-enable interrupts for the next cycle and return to the main thread, which should still be waiting. And that's all we need to do for the code. We're going to deploy this as a snapshot named irq.sna, and to generate that, we have a build script. We simply call sjasm plus with the lst option to generate a machine code listing, and then pass it the name of our assembly file, irq.asm. Now let's go to the terminal and run it. We run build.sh, then do a directory listing and see that irq.sna is right there. So let's load it into the emulator. We're using Fuse again, so we hit F3 and select irq.sna and let it run. There's our sprite right in the middle of the display. If we hold down Z, it starts moving to the left, and then holding down X gets it moving to the right. As you can see, the animation is nice and smooth thanks to the interrupt timing. Obviously, there's a lot more you can do with this, and I strongly encourage you to try modifying the sprite, the way it moves, and maybe even add some additional graphics to place around it, instead of just blank paper. In the linked GitHub repo, you'll find not only this code, but all of the code examples for each lesson, and all the slides presented in this series. In the README, you'll also find links to some additional materials that can help explain what's going on, and provide some needed background in case your programming experience is a bit limited. Please subscribe to my channel and click the bell to be notified when the next episode comes out, and please like this video if you learned anything, and let YouTube know that you want to see more tutorials like this. If you can't wait for the next episode to go public, join our Patreon community and see my videos ad-free as soon as they are uploaded, just like the people you see here. Thanks for watching, and I hope to see you again soon. Bye-bye.